Hello everyone. Today we'll study the natural exponential function. What is the natural exponential function? Here, let me introduce it step by step. First of all, let f of x equal to ln of x. That's called a natural logarithmic function. Then from last class, we know that its graph looks like this. From last class, we know that its graph looks like this. It goes through 1 here. It goes through 1 in the x-axis. On the left side here, when s approaches to 0 from right side, the limit goes to negative infinity. On the right side here, when s goes to infinity, the limit goes to infinity. That's the function y equal to ln of x. And from the graph, we know that the domain of the function is from 0 to infinity, not including 0. The domain of the function is from 0 to infinity, not including 0. How about the range of f? How about the range of the function? We know that on the left side, it goes down to negative infinity. On the right side, go up to infinity. And f is continuous. So the range of the function is from negative infinity to infinity, the entire y-axis. The range of f is the entire y-axis, from negative infinity to infinity. On the left side, go down to negative infinity. On the right side, go up to infinity. So the range of the function is from negative infinity to infinity. And also we know that since its derivative, f prime of x is 1 over x, and 1 over x is greater than 0 for all x in the domain, f prime of x is 1 over x, which is greater than 0 for all x in the domain. That means f is always increasing. F is always increasing. If f is always increasing, it passes horizontal line test, then f must be a one-to-one function. If f is a one-to-one function, then f has an inverse function. If f is 1-to-1, then it has an inverse function. So f has an inverse function. Called inverse of f. Inverse of f. Inverse of f map from the range of f to the domain of f. Inverse of f map from range of f to the domain of f. That's range of f. That's domain of f. And its graph looks like this. The graph of the inverse function is symmetrical over the line y equal to x. The graph of inverse function is symmetrical over the line y equal to x. So it goes through, since function f goes through 1 in the x-axis, the inverse function will go through 1 in the y-axis. And since the x-axis is a vertical asymptote, then for the inverse function, the y-axis, since the y-axis is a vertical asymptote, then for the inverse function, the x-axis will be a horizontal asymptote. The inverse function is symmetrical over the line y equal to x. That's the graph of the inverse function. That's the graph of the inverse function. The domain of inverse function is from negative infinity to infinity, and the range of inverse function is from 0 to infinity, not including 0. Next, we try to find the inverse function. What is the inverse function of f? How can we find inverse function of f? Here we know that function f has an inverse function. So by inverse function property, f of inverse f of x equal to x for all x in the range of f. What's the range of f? Here we know that range of function f is the interval from negative infinity to infinity. So f of inverse of f of x is x for all x in the interval from negative infinity to infinity. Hence, f of f inverse of x equal to x for all x in the interval from negative infinity to infinity. Next, let's consider a rational number r. Let r be a rational number. Then we know that r is in the interval from negative infinity to infinity. So we have f of f inverse of r equal to r. Since r is a rational number, r belongs to the interval from negative infinity to infinity. So we can apply this property here. F of f inverse of r equal to r. Also, if I consider f of e to the power r, what do we get? What's f of e to the power of r? Here e is the Euler number. What's f of e to the power of r? For f of e to the power of r, we plug in e to the power of r for x. We plug in e to the power of r for x. So I get ln of e to the power of r. Then, by the rule of logarithm, we can bring exponent to the front. I get r times ln of e. We know that ln of e is 1. They also equal to r. Since f is a one-to-one function, and f of f inverse of r equal to r, which is the same as f of e to the power of r. Since f is a one-to-one function, and both f of f inverse of r equal to f of e to the power of r. If f is a one-to-one function, then what's inside must be exactly the same. What's inside the parentheses must be exactly the same. Then f inverse of r equal to e to the power of r for all rational number r. So f inverse of r equal to e to the power of r for all rational number of r. So this suggests that the inverse function of f is e to the power of x. This suggests the inverse function of x, the inverse function of f, is e to the power of x. Next, let me introduce the natural exponential function. Then the function e to the power of x be the inverse function of the natural logarithmic function ln of x. Then the function e to the power of x is called a natural exponential function. That's how we define a natural exponential function. Here, since the function e to the power of x is the inverse function of the natural logarithmic function ln of x, then by inverse function properties, we have the following. Note, if I let f of x be the natural exponential function, then by the inverse function properties. We have the following. First of all, the domain of the natural exponential function is what? Since the domain of natural logarithmic function is from 0 to infinity, and the range is from negative infinity to infinity, then for the inverse function, the domain and range will be switched. So the domain of the natural logarithmic function, domain of the natural exponential function will be the interval from negative infinity to infinity, and the range of the natural exponential function will be the interval from 0 to infinity. So that's the domain, that's the range of the inverse function. So domain of natural exponential function is from negative infinity to infinity. The range of natural exponential function is the interval from 0 to infinity, which means this function is always positive. The natural exponential function is always positive. Next, since the natural exponential function is the inverse function of the natural logarithmic function, that means if I plug in the natural exponential function into the natural logarithmic function, I get x, since they are inverse function of each other. If I plug in the inverse function into the function itself, I get x. And also, if I plug in the function itself into the inverse function, I also get x. If I plug the function into the inverse function, if I plug in Ln of x for x, I also get x. That's a property of inverse function. Also, since the natural logarithmic function is always increasing, it's continuous, and it's always increasing, then the natural exponential function is always continuously increasing. Since the natural logarithmic function is always continuously increasing, then its inverse function is also continuously increasing. The inverse function f of x equal to e of x is always continuously increasing on the interval, on the domain from negative infinity to infinity. Since the natural logarithmic function is always continuously increasing, its inverse function is also continuously increasing on the domain, which is from negative infinity to infinity. Next, the limit. For the limit as approaches to negative infinity, since this is the inverse function of natural logarithmic function, we can see that here. For natural logarithmic function, the y-axis is a vertical asymptote. That means for the inverse function, the s-axis will be a horizontal asymptote. Since this is a horizontal asymptote, when s approaches to negative infinity, the function approaches to 0. As x approaches to negative infinity, the function approaches to 0. So, as s approaches to negative infinity, the natural exponential function approaches to 0. How about limit s approaches to infinity? We know that the natural exponential function is continuously increasing, and the range is from 0 to infinity. That means when s approaches to infinity, the function eventually goes up to infinity. So as s approaches to infinity, the function eventually approaches to infinity. So for the natural exponential function, when s approaches to negative infinity, the limit is 0. When s approaches to infinity, the limit is infinity. Those are the properties of natural exponential function. Next, let's look at some examples. Evaluate each of the following limits. First limit. Limit as s approaches to 3 from left side. e to the power of 1 over x minus 3. What's this limit? When x approaches 3 from left side, means x is a little less than 3. If x is very, very close to 3, but a little less than 3, a number less than 3 minus 3 is negative, but this number is very, very close to 0. So I get e to the power of 1 over 0, but this limit is from left side. This number is very, very close to 0, but it's a little less than 0. And then we know that 1 divided by a very, very small number is infinity. Positive number divided by negative number is negative infinity. 1 divided by a very, very small number is infinity. And positive number divided by negative number is negative infinity. And we know that e to the power of negative infinity is 0. E to the power of negative infinity is 0. So this limit is 0. Next example. Limit as x approaches to 0 from right side. E to the power of 1 minus ln of x. How can we take this limit? We know that as x approaches to 0 from right side, the natural logarithmic function approaches to negative infinity. And here, 1 minus negative infinity approaches to infinity. 1 minus negative infinity approaches to positive infinity. E to the power of infinity. We know that e to the power of infinity is infinity. So this limit is infinity. Next example. Limit as x approaches infinity. E to the power of sine of 1 over x. E to the power of sine of 1 over x as x approaches infinity. We know that as x approaches infinity, 1 over infinity approaches to 0. We get e to the power of sine of 0. Sine of 0 is 1. Sine of 0 is 0. E to the power of 0 is 1. So this limit is 1. Next example. Limit as x approaches to 0 from the right. Inverse tension of Ln of x. We know that as x approaches to 0 from the right, the natural logarithmic function approaches to negative infinity. And inverse tension of negative infinity, if you look at the picture, that's the graph of inverse tension. That's the graph of inverse function. Horizontal asymptote here is negative pi over 2 and positive pi over 2. So as s approaches to negative infinity, inverse tension approaches to negative pi over 2. So this limit is negative pi over 2. Inverse tension of negative infinity approaches to negative pi over 2. Next example. Limit as s approaches to infinity, Ln of e to the power of x plus x squared. How can we take this limit? We know that as s approaches to infinity, e to the power of x also approaches to infinity. And infinity squared is also infinity. We have Ln of infinity. And we know that Ln of infinity is infinity. As s approaches to infinity, the natural logarithmic function approaches to infinity. That's the answer to this limit. Next. Limit as s approaches to infinity. 2e to the power of x plus 1 over 3e to the power of x minus 1. How can we take this limit? We know that as s approaches to infinity, e to the power of x also approaches to infinity. So in the numerator, infinity plus 1 is infinity. In the denominator, as s approaches to infinity, e to the power of x also approaches to infinity. So we get infinity minus 1, which is also infinity. In the case of infinity over infinity, this is called indeterminate form. So we can take derivative directly. We need to simplify first. What can we do here? For this limit here, I can try to divide every term by e to the power of x. If I divide every term by e to the power of x, I get 2e to the power of x over e to the power of x plus 1 over e to the power of x over 3e to the power of x over e to the power of x minus 1 over e to the power of x. Then simplify. We can cancel e to the power of x from top and bottom. From top and bottom, what's left is limit as s approaches to infinity, 2 plus 1 over e to the power of x over 3 minus 1 over e to the power of x. We know that as s approaches to infinity, the natural exponential function also approaches to infinity. 1 over infinity is 0. 1 over infinity is 0. So we get 2 plus 0 over 3 minus 0, which is 2/3. That's the limit. Next, let me introduce laws of exponents. Let x and y be any real numbers, and let r be a rational number. Then we have the following laws. First law says e to the power of x times e to the power of y. That's e to the power of s plus y. When we multiply two natural exponential functions, we add exponent. Second law says e to the power of x over e to the power of y equal to e to the power of s minus y. Second law says when we divide two natural exponential functions, we subtract exponent. Keep the base the same, subtract exponent. The third law says e to the power of x raised to the power of r equal to e to the power of sr. Now, let's prove the laws. For the first law, we try to prove left side equal to right side. We try to prove left side equal to right side. We try to use the law of logarithms to prove the law of exponents. So, for law of logarithm, we apply log on both sides first. Then we apply log on the left side. Ln of e to the power of x times e to the power of y. By the first law of logarithm, I can write it as, I can convert multiplication to addition. Write it as ln of e to the power of x plus ln of e to the power of y. That's the first law of logarithm. I can convert multiplication to addition. Then, by the inverse function property, we know that ln and e, they are inverse function of each other, they get cancelled. We get x. ln and e, they are inverse function of each other, they get cancelled. We get y. So, ln of ex times ey equal to s plus y. Next, we try to eliminate ln, make the left side look like this. What I can do is, I can apply function e on both sides. Apply function e on both sides. Apply function e on both sides. Then, on the left side here, since e and ln they are inverse function, then by inverse function property they get cancelled. We get e to the power of x times e to the power of y equal to e to the power of s plus y. That's the proof of the first law. Proof of the second law is very, very similar. I first apply natural log on both sides, on the left side. I first apply natural log on the left side. I get natural log of e to the power of x over e to the power of y. By the second law of logarithm, I can convert division to subtraction. By the second law of logarithm, I can convert division to subtraction. Write it as ln of e to the power of x minus ln of e to the power of y. That's the second law of logarithm. Then, since ln and e they are inverse function of each other, they get cancelled. Since ln and e they are inverse function of each other, they get cancelled. So I get ln of e to the power of x over e to the power of y equal to s minus y. Next, we try to eliminate ln on the left side. So apply function e on both sides. Okay. E to the power of ln of e to the power of x over e to the power of y equal to e to the power of s minus y. Apply function e on both sides, which means plug both sides to function e. Plug both sides into the natural exponential function. Then, by inverse function property, I cancel e and ln. Since they are inverse of each other, I cancel inverse function e and ln. So on the left side, what's left is e to the power of x over e to the power of y. That's the left side. On the right side, we get e to the power of s minus y. That's the proof of the second law. Proof of the third law is very, very similar. We try to use the third law of logarithm to prove the third law of exponent. I first apply natural log on both sides, on the left side. So I get natural log of x e to the power of x to the power of r. I first apply natural log on the left side. Then, by the third law of logarithm, since r is a rational number, I can bring r to the front. By the third law of logarithm, since r is a natural number, I can bring r to the front. I get r times ln of e to the power of x. Bring r to the front. By the third law of logarithm, you can bring exponent to the front. And then we know that since ln and e, they are inverse function of each other, they get cancelled. By inverse function property, they get cancelled. So we get r times x. Since ln and e get cancelled, we get r times x. So ln of e to the power of x to the power of r equal to this. Next, we try to eliminate ln on the left side. So apply function e on both sides. Apply function e on both sides. I get e to the power of ln of e to the power of x to the power of r equal to e to the power of r times x is the same as sr. R times x is the same as sr. Then, by inverse function properties, function e cancels function ln. What's left on the left side is e to the power of x raised to power r. On the right side is e to the power of sr. That's a proof of the third law. And in general, the third law is also true when r is a real number. The third law is also true when r is a real number. We'll give a proof in next section. In general, the third law is also true when r is a real number. Not only rational number, the third law is also true when r is a real number. We'll give a proof in next section. Next, let's look at some examples. Simplify each of the following expressions. First expression, e to the power of ln of 3. How can we simplify? Since e and ln, they are inverse function of each other, then by the inverse function property, they get cancelled. The answer is 3. Since e and ln, they are inverse function of each other, they get cancelled. Answer is 3. Next example, e to the power of 2 times ln of 5. Here we can consider 2 as a coefficient of ln function. Then, by the third law of logarithm, we can bring the coefficient back as exponent. So this expression can be rewritten as e to the power of ln of 5 squared. By the third law of logarithm, we can bring 2 back as exponent. Then here, e and ln, they are inverse function of each other. By inverse function property, they get cancelled. We get 5 to the power of 2, which is 25. So that's the answer to this expression. Next example, e to the power of ln of 4 plus ln of 3. E to the power of ln of 4 plus ln of 3. How can we simplify this expression? We have e to the power of ln of 4 plus ln of 3. By the first law of exponent, this expression can be rewritten as e to the power of ln of 4 times e to the power of ln of 3 by the first law of logarithm. By the first law of exponent, I can write e to the power of s plus y as e to the power of x times e to the power of y by the first law of exponent. Then we know that since e and ln they are inverse function of each other, by inverse function property, function e cancels function ln. What's left is 4 times 3, and we know that 4 times 3 is 12. Next example, e to the power of 4 ln of 3 minus 1. How can we simplify this expression? By the second law of exponent, we know that e to the power of s minus y can be rewritten as e to the power of x over e to the power of y. By the second law of exponent, this expression can be rewritten as e to the power of 4 ln of 3 over e to the power of 1. On the numerator, e to the power of 4 ln of 3. If we consider 4 as a coefficient of the natural logarithmic function, then by the third law of logarithm, we can bring the coefficient back as exponent. So the numerator can be rewritten as e to the power of ln 3 to the power of 4. By the third law of logarithm, we can bring the coefficient back as exponent. Then on the top here, e and ln, they are inverse function of each other, they can cancel. What's left is 3 to the power of 4. And we know that 3 to the power of 4 is 81. That's the numerator. On the denominator, e raised to power 1 is e. So the final answer is 81 over e. That's how we simplify this expression. Next example, solve each of the following equations. First equation, 2 times e to the power of 2x plus 5 equals 13. In the equation, if it contains exponential function, try to isolate exponential function first. So here I can subtract 5 from both sides first. I get 2 times e to the power of 2x equal to 8. Then I can divide both sides by 2. If I divide both sides by 2, I get e to the power of 2x equal to 4. Next, we take x by itself, which means we need to eliminate e. So here I can apply ln on both sides. If I apply function ln on both sides, I get ln of e to the power of 2x equal to ln of 4. We know that ln and e, they are inverse function of each other. By inverse function property, they can cancel. By inverse function properties, they can cancel. So we get 2x on the left side. Since ln and e can cancel, we get 2x by itself on the left side. Right side is ln of 4. Then I can divide both sides by 2. I get s equal to half ln of 4. That's the final answer. But if we want to simplify further, ln of 4 can be rewritten as 2 squared. ln of 4 can be rewritten as 2 squared. Then, by the third law of logarithm, we can bring the exponent to the front. If I bring exponent to the front, 2 times half, they can cancel. Answer is ln of 2. This is not necessary. If we want to simplify further, we can do this. This is not necessary. That's the final answer. Next example, e to the power of 2x minus 4 times e to the power of x minus 5 equal to 0. How can we solve this equation for x? We can try to solve this equation by factoring. It looks hard to factor, so let's make one substitution. If I let u equal to e to the power of x, then if I square both sides, u squared will be e to the power of x squared. Then by the third law of exponent, I can multiply. 2 times x is 2x. So u squared is the same as e to the power of 2x. Then substitute. E to the power of 2x is u squared minus 4 times e to the power of x. E to the power of x is u minus 5 equal to 0. Next, we can factor. This expression can be factored as u minus 5 times u plus 1 equal to 0. Solve the equation, we get u equal to positive 5, u equal to negative 1. Here, u is e to the power of x. So we have e to the power of x equal to 5, and e to the power of x equal to negative 1. We know that the domain of the natural exponential function is from 0 to infinity, which means the range of natural exponential function is from 0 to infinity. Since the range of the natural exponential function contains only positive numbers, e to the power of x cannot be negative 1. So this answer must be rejected. Since natural exponential function is always positive, it cannot be negative 1. This answer is rejected. Solve the other solution, solve the other equation for x. Here we try to get x by itself. That means we need to eliminate e. So I can apply natural log on both sides. If we apply natural log on both sides, we get ln of e to the power of x equal to ln of 5. And then, since natural log and natural exponential, they are inverse functions of each other, they can cancel. We have x by itself on the left side. Since they are inverse functions, by inverse function properties, they can cancel. We have x by itself on the left side. On the right side, we leave it the same. So s equal to ln of 5. That's the solution to this equation. Next example. Natural log of 2x minus 5 equal to 2. How can we solve this equation for x? How can we get s by itself? In this equation, in order to get s by itself, we need to eliminate ln first. So we can apply e on both sides. Apply function e on both sides. We get e to the power of ln of 2x minus 5 equal to e to the power of 2. Apply e on both sides. Then on the left side here, e and ln, they are inverse function of each other, they can cancel. What's left is 2x minus 5. On the right side, e squared stays the same. Next, we try to get s by itself. So I can add 5 to both sides. I get 2s equal to e squared plus 5. Then I can divide both sides by 2. I get s equal to half of e squared plus 5. That's the solution to this equation. Next example. ln of x plus 1 equal to ln of x plus 1. How can we solve this equation for x? So in order to solve the equation for x, we try to eliminate ln first. So here I can apply function e on both sides. Apply function e on both sides. We get e to the power of ln of x plus 1. Apply function e on both sides. E to the power of ln plus 1 equal to e to the power of ln of s plus 1. Remember, they are not the same. Left side and right side here, they are not the same. This s plus 1 has parentheses. This is ln of x plus number 1. This is ln of x plus 1. They are not the same. Now, for the left side here, we can use the first law of exponent. This expression can be rewritten as e to the power of ln of x times e to the power of 1. By the first law of exponent, this expression can be rewritten as e to the power of ln of x times e to the power of 1. Let's temporarily leave the right side the same. Next, since e and ln, they are inverse functions of each other, by inverse function properties, they can cancel. So we get s by itself. E and ln can cancel, we get s by itself. E to the power of 1 is e. On the right side, e and ln, they are inverse functions of each other. They can cancel. What's left is s plus 1. Next, we try to get s by itself. So I can subtract x from both sides. I get ex minus x equal to 1. Next, I can factor power x. If I power x, I get e minus 1 equal to 1. Then I can divide both sides by e minus 1. I get s equal to 1 over e minus 1. That's the solution to this equation. Next, let me introduce the derivative of the natural exponential function. How can we take derivative for natural exponential functions? For example, if f of x is e to the power of x, how can we take derivative for this function? We cannot take derivative for this function directly. So let me first of all apply Ln on both sides. If I apply Ln on both sides, I get Ln of f of x equal to Ln of e to the power of x. Since Ln and e, they are inverse functions of each other, by inverse function property they get cancelled. So we have Ln of f of x equal to x. Next, take derivative on both sides. Use implicit differentiation. Take derivative on both sides. If I take derivative on the left side here, I get 1 over f of x times f prime of x by chain rule. 1 over the inside function times the derivative of the inside function by chain rule. Then on the right side, derivative of x is 1. If I take derivative for x, I get 1. Then solve an equation for f prime of x. Solve an equation for f prime of x. Here I can multiply both sides by f of x. Multiply both sides by f of x. I get f prime of x equal to f of x, which means f prime of x equal to e to the power of x. So the derivative of e to the power of x stays the same. The derivative of e to the power of x stays the same. So derivative of the natural exponential function stays the same. Keep it in mind. Derivative of e to the power of x stays the same. Also, if we have derivative of e to the power of some other functions, then by chain rule, we first of all rewrite the function e to the power of f of x times the derivative of the exponent by chain rule. So keep this formula in mind. That's how we take derivative for natural exponential function. Derivative of e to the power of x stays the same. Derivative of e to the power of f of x, if the exponent is not x, it's something else, we copy the function first. When we take derivative, copy the function first, then times the derivative of the exponent. Next, let's look at some examples. Differentiate each of the following functions. First function, f of x equal to e to the power of s squared minus s cubed. How can we take derivative for this function? According to the formula, when we have e to some other functions here, we copy the function first. When we take derivative, copy the function first, then times the derivative of an exponent by chain rule. So copy the function first, I get e to the power of s squared minus s cubed. Then by chain rule, times the derivative of an exponent, I get 2x minus 3s squared. That's the derivative of this function. Next example, f of x is e to the power of x times sine x. F of x is e to the power of x times sine x. How can we take derivative for this function? According to the formula, when we have e to some other function here, when we take derivative, copy the function first, and then times the derivative of the exponent. So I copy the function first. I get e to the power of x times sine x. Then times the derivative of the exponent. For the derivative of exponent here, we need to use product rule. We have x times sine x. Use product rule. Product rule says derivative of the first times the second plus the first times derivative of the second. That's the derivative of this function. Next example, f of x equal to e to the power of x times ln of x. How can we take derivative for this function? When we have two functions multiplied together, use product rule. When we have two functions multiplied together, use product rule. So product rule says derivative of the first, derivative of e to the power of x stays the same. So derivative of the first stays the same, times the second plus the first times the derivative of the second. So that's the derivative of this function using product rule. Next example, f of x equal to x squared times e to the power of x squared. X squared times e to the power of x squared. How can we take derivative for this function? When we have two functions multiplied together, use product rule. When we have two functions multiplied together, use product rule. So product rule says derivative of the first times the second plus the first times derivative of the second. When we have e to some function here, we copy the function first, then times the derivative of an exponent, which is 2x. That's the derivative of this function. Next example, f of x equal to e to the power of sine x minus cosine x. How can we take derivative for this function? According to the formula, we have e to some function here. Copy the function first. When we take derivative, copy the function first, then times the derivative of the exponent. So copy the function first. We get e to the power of sine x minus cosine x times the derivative of the exponent. Derivative of sine x is cosine x minus derivative of cosine x. Derivative of cosine x is negative sine x. So like a positive sine x. That's the derivative of this function. Next example, f of x is e to the power of 2x plus 1 over e to the power of 3x minus 1. These ones, they are not part of exponent. These ones, they are terms. They are not part of an exponent. So how can we take derivative for this function? When we have a function divided by another function, we need to use quotient rule. When we have a function divided by another function, when we take derivative, we need to use quotient rule. Quotient rule says the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom square. Derivative of the top times the bottom minus the top times the derivative of the bottom square. So use quotient rule here. Derivative of the top is e to the power of 2x times 2. Derivative of 2x is 2. Derivative of 1 is 0. That's derivative of the top times the bottom e to the 3x minus 1 minus the top e to the 2x plus 1 times derivative of the bottom. For derivative of the bottom, we have e to the 3x times 3. Derivative of 3x is 3. Derivative of 1 becomes 0. Over the bottom square, which is e to the 3x minus 1 squared. That's the derivative of this function using quotient rule. Next, let me introduce the antiderivative of the natural exponential function. How can we take antiderivative from the function e to the power of x dx? We know that derivative of e to the power of x stays the same. Then the antiderivative of e to the power of x also stays the same. So the antiderivative of e to the power of x dx stays the same. It's e to the power of x plus c. That's the formula for an antiderivative of the natural exponential function. Next, based on this formula, let's do some examples. Evaluate each of the following integrals. First example, integral of x times e to the power of x squared dx. How can we take antiderivative for this function? It looks like it cannot be done directly. Since we can't find antiderivative directly, let's try to apply U substitution. For U substitution, if I let U be x squared, then my du will be 2x dx. We have x dx. We miss a 2 here. We're missing a 2. So 2 is a constant. Here 2 is a constant. I can divide both sides by 2. That's not a big problem. I can divide both sides by 2. Make half of du equal to x dx. Then this integral can be rewritten as e to the power of x squared times x dx. Then substitute. X squared is u. X times dx is half of du. Then half is constant. I can put it outside. I get integral of e to the power of u du. We know that integral of e to the power of x stays the same. So integral of e to the power of u also stays the same. The answer is half of e to the power of u plus c. And then for the final answer, replace u with x squared. So the final answer is half of e to the power of x squared plus c. That's the final answer. Next example. Integral of secant x times tangent x times e to the power of secant x times dx. How can we take antiderivative for this function? Since we are not able to find antiderivative directly, let's think of U substitution. For U substitution, if I let U be secant of x, then my du will be secant x times tangent x dx. We have secant x, tangent x here, so this substitution works. This function can be rewritten as e to the power of secant x times secant x tangent x dx. Then substitute. We have e to the power of u, secant x is u, times secant x times tangent x dx. Secant x tangent x dx is du. So we get e to the power of u times du. Then take antiderivative. Antiderivative of e to the power of u stays the same. I get e to the power of u plus c. Then for the final answer, replace u with secant x. The final answer is e to the power of secant x plus c. Next example. How can we take integral for e to the power of negative 4x dx? Since we can't find the antiderivative directly, let's apply U substitution. For U substitution, if I let u be negative 4x, then du will be negative 4 dx. We have dx here. What's missing is negative 4, but that's a constant. It's not a big problem. I can divide both sides by negative 4. If I divide both sides by negative 4, I get negative 1 over 4 du equal to dx. Then substitute. We get e to the power of u times dx. Dx is negative 1 over 4 du. Dx is negative 1 over 4 du. And we know that negative 1 over 4 is a constant. I can pull it outside. If I pull out negative 1 over 4, I get integral of eu du. Then take antiderivative. Antiderivative of e to the power of u stays the same. Then add constant c. For the final answer, replace u with negative 4x. That's the final answer to this integral. Next example. How can we take integral from the function e to the power of 2x plus e to the power of 4x over e to the power of x dx? This problem looks tricky, but if we think of this way, it's not hard. If we think of e to the power of 2x over e to the power of x plus e to the power of 4x over e to the power of x dx, Then, by exponential rule, when we divide with such an exponent, 2x minus x, we get e to the power of x. By exponential rule, when we divide with such an exponent, 4x minus x is 3x. Then we can split this into two integrals. Integral of e to the power of x dx plus integral of e to the power of 3x dx. Take each integral individually. For the first integral, antiderivative of e to the power of x stays the same. So for the first integral, the antiderivative stays the same. For the second integral, apply u substitution. Let u be 3x. Then du will be 3 times dx. We have dx here. What's missing is the number 3. Number 3 is a constant. I can divide both sides by 3. So I get 1/3 of du equal to dx. Then substitute. I get integral of e to the power of u times 1/3 of du. Then 1/3 is a constant, I can put it outside. If I put 1/3, I got integral of eu du. And then we know that integral of e to the power of u stays the same. I get 1/3 of e to the power of u. Then I can replace u with 3x. I get 1/3 of e to the power of 3x. That's the antiderivative of this function. So for the final answer, I take e to the power of x plus 1/3 of e to the power of 3x plus c. So for the final answer, add this together, I get e to the power of x plus 1/3 of e to the power of 3x plus c. That's the final answer to this integral. Next example. How can we take integral from the functions 1 plus e to the power of negative 2x to the power of 2? How can we take integral from this function? This one is tricky. We need to expand the perfect square first. If we expand the perfect square, remember the formula is a plus b squared equal to a squared plus 2ab plus b squared. If we expand this perfect square, we get 1. Plus 2 times e to the power of negative 2x plus e to the power of negative 2x squared. What's e to the negative 2x squared? By the third exponential rule, we can multiply exponents. That's integral of 1 plus e to the 1 plus 2 times e to the power of negative 2x plus e to the power of negative 4x. When we have negative 2x times to the power of 2, by the third exponential rule, we multiply exponents. Negative 2x times 2 is negative 4x. Then take integral for each term individually. We have integral of 1 dx plus integral of 2e raised to 2x dx plus integral of e raised to negative 4x dx. Take each integral individually. For the first integral, antiderivative of 1 is x. That's easy. For the second integral, make u substitution. Let u be negative 2x. Then du is negative 2 dx. We have dx. We miss the negative 2. So I can divide both sides by negative 2. Okay, negative 1 over 2 du equal to dx. Then substitute. Number 2 stays the same. E to the power of negative 2x. Negative 2x is u times dx. Dx is negative half du. Then multiply. 2 times negative half is negative 1. Negative 1 is a constant, I can put it outside. 2 times negative half is negative 1. That's a constant, I can put it outside. E to the power of u stays the same. Then take antiderivative. Antiderivative of e to the power of u stays the same. And then for the final answer, replace u with negative 2x. we get negative e to the power of negative 2x. That's the second integral. Then for the third integral, make another U substitution. In the same problem, use a different letter. Say v equal to negative 4x. In the same problem, for substitution, use a different letter. Here we use u, use v here. The v be negative 4x. Then dv will be negative 4 dx. We have dx here. What's missing is negative 4. Negative 4 is a constant, so I can divide both sides by negative 4. I get negative 1 over 4 dv equal to dx. Then substitute. I get e to the power of v times negative 1 over 4 dv. Here, negative 1 over 4 is a constant, I can pull it outside. If I pull out negative 1 over 4, I get e to the power of v dv. And then take antiderivative. We know that antiderivative of e to the power of x stays the same. So antiderivative of e to the power of v also stays the same. I get e to the power of v. Then replace v with negative 4x. I get e to the power of negative 4x. So for the final answer, add these together. For the final answer, add these three integrals together. The final answer is x minus 2e, x minus e raised to 2x, x minus e raised to negative 2x, minus 1 over 4, e raised to negative 4x plus c. That's the final answer to this integral. Next example. Integral of e to the 2x times 1 plus e to the 2x dx. How can we take this integral? We can try to distribute first. If I distribute e raised to 2x, I get integral of e to the power of 2x plus e to the power of 4x. When we multiply, add the power. When we multiply, add the power by the first exponential rule, add the power. When we multiply, add the power. Then take I can separate the integral, write it as integral of e to the 2x dx plus integral of e to the 4x dx. Then make u substitution for each of them. Make u substitution for each of them. For the first integral, I let u equal to 2x. Then du will be 2 dx. We have dx here. What's missing is a 2. So I can divide both sides by 2. I get half of du equal to dx. Then substitute. I get e to the power of u times half of du. Half is a constant. Half is a constant. I can put it outside. If I pull out half, I get e to the power of u du. Then take antiderivative. We know that antiderivative of e to the power of u stays the same. Then for the final answer, replace u with 2x. That's an answer to the first integral. For the second integral, do the same thing. Use u substitution. Here, pick different number, different letter. Say v. The v be 2x. The v be 4x. Then dv will be 4 dx. We have dx here. What's missing is a 4. 4 is a constant, so I can divide both sides by 4. I get 1 over 4 dv equal to dx. Then substitute. I get e to the power of v times dx. dx is a quarter of dv. Quarter 1 over 4 is a constant. I can put it outside. If I pull out 1 over 4, I get e to the power of v dv. Then take antiderivative. Antiderivative of e to the power of v stays the same. I get 1 over 4 e to the power of v. And then for the final answer, replace v with 4x. I get 1 over 4 e to the power of 4x. So for the final answer, add these two integrals together. For the final answer, add these two antiderivatives together. We get 1/2 e to the 2x plus 1 over 4 e to the 4x plus c. That's the final answer to this integral. Next example, integral of e to the 2x times 1 plus e to the 2x raised to power 10 dx. What can we do here? 1 plus e to the power of 2x raised to the power of 10. We don't want to expand this, that's too much work. So since we can find antiderivative directly, and we can expand this, we can try u substitution. Let u be the inner function 1 plus e to the 2x. If I let u be 1 plus e to the 2x, what's du? 1 is a constant, its derivative is 0. If I take derivative for e to the 2x, I get e to the 2x times 2 times dx. We have e to the power of 2x. We have dx. What's missing is a 2. But 2 is a constant, it doesn't matter. We can divide both sides by 2. If I divide both sides by 2, I get 1 over 2 du equal to e to the 2x dx. So this function can be rewritten as 1 plus e to the 2x raised to the power of 10 times e to the 2x dx. Then let's substitute. If I substitute, 1 plus e to the 2x is u. I get u to the power of 10. E to the 2x dx is half of du. Here, half is constant, I can put it outside. I get 1 over 2 times the integral of u to the power of 10 du. Then take antiderivative using power rule. I get half of u to the power of 11 over 11 plus c. Simplify, we get 1 over 22 times u to the power of 11. Plus c. For the final answer, replace u with 1 plus e to the 2x. For the final answer, replace u with 1 plus e to the 2x to the power of 11 plus c. That's the final answer to this integral. Next example, integral of 1 over e to the power of x times 4 plus e to the power of negative x raised to the power of 3 times dx. How can we find antiderivative for this function? Since we can find the antiderivative directly, let's think of u substitution. What can we choose for u? Let's try. If I let u be 4 plus e raised to negative x, what do I get? If I let u be 4 plus e raised to negative x, what's my du here? For my du, take derivative for this function. I get e raised to negative x times negative 1 dx. If I simplify this expression, I have du equal to 1 over e to the power of x times negative 1 times dx. We have e to the power of x on the bottom. We have dx. What's missing is a negative 1. So I can divide both sides by negative 1. I get negative du equal to 1 over e to the power of x dx. Then this function can be rewritten as 1 over 4 plus e raised to negative x to the power 3 times 1 over e to the power of x times dx. Then substitute. The denominator 4 plus e raised to negative x, that's u. So you get u to the power of 3 on the bottom. 1 over e to the power of x dx, that's negative du. Then I can pull out negative sign. That's a constant. We can treat this as negative 1. That's a constant, pull it outside. 1 over u to the power 3 can be written as u raised to negative 3 du. Then take antiderivative. We get negative u raised to negative 2 over negative 2 plus c. Here, double negative become positive. I can bring u from top to bottom and make exponent positive. So I get 1 over 2u squared plus c. Double negative become positive. I bring u raised to negative 2 from top to bottom, make exponent positive. And then replace u with 4 plus e raised to negative x. That's the final answer to this integral.